Welcome back. It looks like you got your SOLIDWORKS Flow Simulation tab up, and you'll see mine is highlighted up here. There's a lot of different ways to do flow simulation, and flow simulation is really doing what we call computational fluid dynamics. It's doing some fairly complex mathematics to determine how fluid flows either through an internal body or around a body. That's an external study. So let's go ahead and click on your flow simulation tab. I recommend the first few times we do this, use the wizard, and I'm going to show you how to use the wizard. So let's go ahead and select the wizard. And up here, let's give it some detail. This first project we're going to do is going to be a 10 degrees angle attack. So I'm just going to type 10 AOA, and then in the descriptive button, or box rather, I'm going to put the comments of 10 AOA, 50 miles per hour. Click on the next button. Here you can select our units. Let's just leave it at SI. Click the next button. Here we have to choose whether we're internal or external. We want an external condition, and it looks like the top graphic right here, where the wind, or the gas rather, is flowing around our body. And I really should say fluid. It's flowing around our body. Click the next button. Now we have to choose what fluid. Now we're obviously using a gas because we use the air. And when I come down to gases, I can see there's predefined air. I highlight it, but to add it, I have to click the Add button. It then appears down here in the project fluids. Don't worry about the high Mach number or humidity. Leave those unchecked. I'll click Next. We don't have to select anything. Adiabatic wall means that we're not considering any heat transfer from inside of our flow to the outside or vice versa. So just click Next. So there's no heat transfer considerations here. Now, initial conditions, we need to discuss this. You're going to see our initial conditions here are set up such that we have pretty much a standard day. And by that, I mean we're at 101.325 kPa. You've seen that a couple times before, I'm sure. Also 293.2 Kelvin. That's our standard day temperature. And we're going to look at a parameter for initial condition of velocity. So the velocity we're going to set along the x-axis. So let's click this on the x-axis and just put in 22.5. So that's our initial condition, but our coordinate system we're using, we need to select the right AOA. So let's choose our coordinate system. And you'll notice when I do this, I can't really change anything down in this screen. But what I can do is select my coordinate system, go over to my Feature Manager design tree, and now choose my 10 degrees AOA. You'll see that blue arrow shows up. So that's the way the wind's going to be coming at the wing. Once you've done that, select OK. Now we're done setting up initial conditions, so let's click Finish. Now let's tell the simulation when it should stop running. So come up here to this button, Calculation Control Options. Now the Calculation Control Options, we're going to run this for about 100 iterations, and that comes close enough for our simulation to get some decent results, but it doesn't make it so your computer's going to run for a day to solve it. So just use 100 iterations. Click on Goals, All Goals Convergence, and then Auto Travels. Click OK once you've done that. Now let's select over in our, and this tab right here is called the Flow Simulation Analysis tab. So in that, let's go ahead and select our computational domain. Now you can scroll out and you can see how big this is initially. So initially it's pretty conservative in making it fairly large. We can reduce it by probably about 20%. We don't want to make it so small that we cut off pressure ISO lines, but we also don't want to make it so big that we're computing all day. So there I've just reduced it a little bit. So that's an option. You can reduce your computational size, the domain it's going to work in. Go ahead and do that. Now the next thing that we want to accomplish is our goals. So in other words, we want to say, what do we want to solve for? So right click, and you're going to see Insert Global Point Surface Volume and Equation Goals. I want a surface goal. And I really want to look at my wing surface conditions here, because that determines how we make lift. So I have to tell it what surface I want to look at. So I click on the wing, and that's the upper and bottom surface of the wing. And then I want to click both the left and the right surface. So it solves it all the way around. Now the next part of this is really to say what surface or what conditions do I want it to be solving for. So I'm going to expand this back so it's a little easier for you to read. And what you're going to see is there's a min, a max, and an average, and a bulk average. And we're going to generally do the min, max, and average for several different conditions. The first one is I want to do my static pressure, min, average, max. I also want to do my dynamic pressure. So right here, min, average, max. And if I added those two together, I'd get my total pressure, wouldn't I? Don't worry about temperatures anywhere down here. Draught rate, density of the fluid, we don't need to compute for that. But let's look at some velocities here. That's the overall velocity vector in 3 dimensions. Break it into x, break it into y, break it into z. There will be some flow out of the screen at you. Let's also look at Mach number, just for grins. And let's look at, well, we'll leave our turbulence deselected and all of our forces. So let's just leave it there for now. Okay, so I've set up these conditions. I'll give you a second to take a quick look at them. Now click the check mark. We're now ready to start running our simulation. So a quick recap, we set up some different conditions here for some geometry at 10 degree AOA, at 25 degree AOA. We've set up a container that bounds our wing where we're going to look at the fluid flow of it, and it looks pretty darn close to what our wind tunnel looked like. We've also set up some goals to solve for, and we've set up some computational controls here, when to stop. When I've done all that, go ahead and click Run. Don't worry about changing the mesh. We want to use Solve, and we also want to use a new calculation every time we do this. Run it on this computer, use all the cores. When I click Run, what you're going to see pop up here in just a second is this little screen. And you'll see right now it started the processing, and it's kind of telling you how much time it has left. So right now it's getting ready to run calculations. I'm running this on a fairly old computer, so yours may run faster. It tells me I got about 1 minute and 25 seconds left. It's going up. It's probably going to be about 3 or 4 minutes. So once it gets underway for a ways, it'll tell me how much time it has left. So about 2.5 minutes. You'll see it tells you the iterations running right here. Now the second thing I can do here, which is kind of neat, and I'm going to go ahead and add in here. I want to add in some views of the pressure contours. So let's go ahead and add a view, and then I'm going to look at my pressure and click OK. So there's a view of the pressure, and what you'll see right away is you'll notice that I've got a lower pressure on the top than I have on the bottom. Hey, look at that's that lift being computed. You'll also probably see some dynamic pressure from the wing. That's that deflective force on the bottom. So it looks like it's starting to fly there at 10 AOA. I'm going to minimize that. I can also add one that has a setting of velocity and come out here and basically make velocity vectors. And now what I can see in the front plane is now I can see, look at that wind flowing up at it, 10 degrees angle of attack, and following the contour of the line. And notice it's attached pretty well the whole way back. So it looks like a pretty laminar flow condition. So we'll let that run. I'm going to pause the video here, or stop the video, and we'll pick it up after I've got the results. That'll be on my computer in about 3 more minutes.